Alright, so this will be the first video on hyperbolic functions. So there are three main hyperbolic functions here. So the first one is the hyperbolic sine function. So you see that I have SINH. So hyperbolic sine function. If the input is x, then the output of the function is e to the x minus e to the minus x over 2, which can be rewritten as half e to the x minus half e to the minus x. And the domain of this function is the set of all real numbers. The hyperbolic cosine function evaluated at x is equal to e to the x plus e to the minus x over 2, which again can be written as half e to the x plus half e to the minus x. And also the domain here is the set of all real numbers. Notice the difference between hyperbolic sine and hyperbolic cosine. So here there are two, they both have the same two terms. For sine, hyperbolic sine, you have negative in the middle, and for hyperbolic cosine you have plus in the middle. The next hyperbolic function is the hyperbolic tangent of x, which is the hyperbolic sine of x over the hyperbolic cosine of x, which is equal to e to the x minus e to the minus x divided by e to the x plus e to the minus x. Again, the domain is the set of all real numbers. Notice that we have a denominator here, but the denominator is never vanishing, because this denominator is always positive. All right, so we can also, so these are the three main hyperbolic functions that we're gonna be looking at in detail, but there are three others. So we can define hyperbolic cosine of x as 1 over hyperbolic sine of x, which would be, in terms of the exponential function, it's given by 2 over e to the x minus e to the minus x. The domain of this function would be the set of all real numbers except for 0, because when x is 0, the denominator here is 0. Hyperbolic secant of x is defined to be 1 over hyperbolic cosine of x, which is 2 over e to the x plus e to the minus x. Here x could be any real number. Hyperbolic cotangent of x is hyperbolic cosine over hyperbolic sine of x, which is given by this formula here. Again, right here the denominator is 0 when x is 0, so the domain would be all real numbers except 0. Okay, so these are the hyperbolic functions, and they satisfy identities similar to the trig functions. So here I'm going to list out a bunch of identities of hyperbolic functions, and I'm going to prove one of them only, and I'll let you prove the other ones on your own. So the first one says the hyperbolic sine of a negative x is negative hyperbolic sine of x. The second one, hyperbolic cosine of negative x is equal to hyperbolic cosine of x. Third one, hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1. Hyperbolic tangent squared of x plus hyperbolic secant squared of x is equal to 1. Hyperbolic sine of x plus or minus y is equal to hyperbolic sine of x times hyperbolic cosine of y plus or minus hyperbolic cosine of x times hyperbolic sine of y. You can see the similarities between these identities and the identities for the trig functions. Hyperbolic cosine of x plus or minus y is hyperbolic cosine of x, hyperbolic cosine of y, plus or minus hyperbolic sine of x, hyperbolic sine of y. The seventh one is that the hyperbolic tangent of x plus or minus y is hyperbolic tangent of x plus or minus hyperbolic tangent of y over 1 plus or minus hyperbolic tangent of x times hyperbolic tangent of y. The double angle, you have kind of like a double angle formula like in trig functions. So hyperbolic sine of 2x is 2 hyperbolic sine of x times hyperbolic cosine of x. Hyperbolic cosine 2x is hyperbolic cosine squared of x plus the hyperbolic sine squared of x. Notice that this quantity is not 1 like in the case of trig functions. Notice that there is number 3 here, which in the case of trig functions we had a plus here, not a minus. And then hyperbolic cosine squared of x is half of is a half of 1 plus hyperbolic cosine 2x, and hyperbolic sine squared of x is half of hyperbolic cosine 2x minus 1. And hyperbolic tangent of 2x is 2 hyperbolic tangent of x over 1 plus hyperbolic tangent squared of x. Okay, so what I want to do now is kind of prove number 3 right here, and I'm not going to be proving the other ones. I'll let you, none of them are hard. It's just it just doesn't make sense to prove each one of them. So I'm going to be proving number 3 to you. So number 3, I'm going to start with the left hand side. So I want to show that hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. So I'm going to do an algebraic proof, that is, it's a proof by substitution. So what do we know about hyperbolic cosine of x? Well, that's e to the x plus e to the minus x over 2. So I'm plugging that in, squared, minus I'm going to plug in the value of hyperbolic sine of x, which is e to the x minus e to the minus x over 2, and then I have squared. So now it's just a matter of algebraic manipulations. So notice that in this square I'm going to get e to the, I'm going to square the numerator and square the denominator. So the square of the numerator is here and the square of the denominator is 4. Same thing here, we take the square of the numerator and square of the denominator. Now, since we have the same denominator in these two fractions, then when we combine these two fractions, common denominator is 4, and then we get this denominator minus the other, this numerator minus the other numerator here. And now I'm going to expand each of these squares. So here I get e to the 2x plus e to the minus 2x and then plus 2. So if you expand this by using FOIL, you're gonna end up with this. Similarly here, when you square this, you get e to the x, e to the 2x plus e to the minus 2x, and then minus 2. Okay, so now you subtract and simplify, so you can see that e to the 2x and e to the minus 2x, they cancel out. We have a plus 2 here and then another plus 2 coming from here. So that's 4, so I get 4 over 4, which is 1, which is what we wanted to show. Okay, so that concludes the proof of identity number 3 right here. Alright, so now I'm going to list out the derivative formulas for all the hyperbolic functions, and these formulas are similar but not quite exactly the same as in the case of trig functions. So the derivative of the hyperbolic sine is hyperbolic cosine of x. Derivative of hyperbolic cosine of x is hyperbolic sine of x. In the case of trig functions, we had a negative here. Derivative of hyperbolic tangent of x is hyperbolic secant squared of x. The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent of x. The derivative of hyperbolic cosecant of x is negative hyperbolic cosecant of x times cotangent of x. And finally, the derivative of hyperbolic cotangent of x is negative hyperbolic cosecant squared of x. Alright, so again, I'm not going to derive each one of these formulas for you, but let me just derive number 3. So I'm going to show you how to come up with this formula here. That is, I'm going to derive the derivative of the hyperbolic tangent of x. So here it is. Okay, sorry. Okay, all right, so what I'm actually doing first is I'm going to derive number 2 first, and then I'm going to derive 3. I'm not going to derive, so basically we need 1 and 2 in deriving number 3. So I'm going to derive 2, and then the derivation of 1 is similar, and then I'm going to use quotient rule to derive this one. All right, so here it is. What's the derivative of hyperbolic cosine of x? Well, hyperbolic cosine of x is the same as half e to the x plus half e to the negative x. All right, so now we take the derivative of each term. So I get half times the derivative of e to the x, which is itself. And then here I get half times the derivative of e to the negative x. Now the derivative of e to the negative x would be negative e to the negative x. So that's why I'm getting this negative e to the negative x. And there is, of course, half in front. And then that's exactly the hyperbolic sine of x. So the derivative of hyperbolic cosine of x is hyperbolic sine of x. All right, so that's easy. Now I'm going to assume that the derivative of hyperbolic sine is hyperbolic cosine. That's number 1. And now here, how do I derive the derivative of hyperbolic tangent of x? Well, hyperbolic tangent of x is hyperbolic sine of x divided by hyperbolic cosine of x. So now I just apply the quotient rule. So I square the denominator. It's the denominator multiplied by the derivative of the numerator, and the derivative of the numerator here is hyperbolic cosine of x, and then minus the numerator as it is here, and then multiplied by the derivative of the denominator, and the derivative of the denominator here is hyperbolic sine of x. So what am I getting? I'm getting hyperbolic cosine square of x here minus hyperbolic sine square of x here, but we know that this numerator is gonna reduce to 1 by one of the identities that we just have looked at. So we get 1 over hyperbolic cosine square of x, which is hyperbolic secant square of x. So we see that the derivative of hyperbolic tangent of x is hyperbolic secant square of x. Okay, so you just need to memorize these derivative formulas as well as these identities right here. All right, so what I want to do now is look at the graph of the hyperbolic sine function. Before I show you the graph, let me point out some interesting fact about the hyperbolic sine function. So the hyperbolic sine function is given by half e to the x minus half e to the negative x. So what I want you to think about is when x is big, when x is a big number, what is the value of this function approximately? Well, notice that when x is big, so by saying x goes to infinity, I'm saying basically when x is big, when x is big, e to the negative x is very, very small. So when x is big, e to the negative x is very small. So the graph of the value of sine of x would be approximately given by half of e to the x. On the other hand, when x is large in the negative direction, then in that case, e to the x will be close to 0. So when x is negative large, e to the x is close to 0. So the hyperbolic sine function is going to be approximately negative half of e to the negative x. So I hope that makes sense. So graphically what it means is that as x gets bigger and bigger in the positive direction, the graph of hyperbolic sine x gets closer and closer to the exponential function half e to the x, and when x goes to negative infinity, that is, as x gets smaller and smaller in the negative direction, the graph of hyperbolic sine of x gets closer and closer to the graph of the exponential function negative half e to the negative x. So here is okay, by the way, what is hyperbolic sine of 0? So hyperbolic sine of 0 would be half e to the 0 minus half e to the 0, which is going to be half minus a half, which is 0. So hyperbolic sine of 0 is 0. So here's the graph, right? So this is the pink curve here is the graph of the hyperbolic sine function, and the green curve here. Sorry, let's not worry about the green curve yet. The blue curves here. So one of them is, this one is the graph of half e to the x, and the other one here is the graph of negative half e to the negative x. So notice that the graph of the hyperbolic sine of x, which is the pink one, as x goes to infinity, it gets closer and closer to the exponential half e to the x, and when x goes to negative infinity, the graph of hyperbolic sine gets closer and closer to the exponential function negative half e to the negative x. Okay. Now this function hyperbolic sine of x is a one-to-one function. It's in fact an increasing function. So clearly it has an inverse function, and the graph of the inverse of this function will be a reflection of this of the graph of, so the graph of the inverse of the hyperbolic sine function is denoted by hyperbolic sine with the -1 superscript and the evaluated at x here. So this is the symbol for the inverse of this function, and the graph of that is simply the reflection of the graph of the hyperbolic sine across the line y is equal to x. So the green curve here is the graph of the inverse of the hyperbolic sine function, and notice that the green curve is also an increasing function, and so on. All right, so let's recall, because hyperbolic, so this guy is the hyperbolic sine inverse of x. So hyperbolic sine inverse of x is equal to y if and only if hyperbolic sine of y is x, because they are inverses. So basically you reverse the input-output pair. And so the domain of the hyperbolic, so let's recall from the graph here that the domain the domain and the range of the hyperbolic sine of x is the set of all real numbers. So the domain and the range of the hyperbolic sine inverse of x is also the set of all real numbers. And we of course have the cancellation properties. That is, because these two functions are inverses, their composition in any order will give us the identity function. So the hyperbolic sine of hyperbolic sine inverse of x is equal to x, and hyperbolic sine inverse of hyperbolic sine of x is equal to x. This is for any real number x. Okay, so let's look at an example here. So hyperbolic sine of 0 is 0, which we just saw in a minute ago, and therefore hyperbolic sine inverse of 0 would be 0. Hyperbolic sine of ln of 2, what is that? Well, it'll be e to the ln of 2 minus e to the negative ln of 2 divided by 2. Now e to the ln of 2 here the same, minus e to the ln of So here I have e to the minus ln of 2. Now the negative here, by using one of the log properties, we can rewrite that as e to the ln of 2 to the negative 1. Now e to the ln of 2 is the same as 2 by one of the log properties. E to the ln of 2 to the negative 1 is 2 to the negative 1 by the same property. And then I have 2 minus a 2 to the negative 1, which is 2 minus a half. So at the end, if you simplify this, you get 3/4. So hyperbolic sine inverse of 3/4 is ln of 2. Alright, so let's turn our attention to the graph of the hyperbolic cosine of x and the inverse of that.